Hello everyone. In this video we are going to see a demo of transient structural analysis. So transient we call the portion of the behavior that is changing with respect to time until the output reaches its steady state uh, status and keeps basically repeating that one with respect to time, right? So, for example, if you have a vibrating system, right, and you basically provide some external forces or displacements, right, and then let go, then the system will show some transient response. If there is no external force, all you see is transient response, which is basically a function of the natural frequencies and the damping in the system. If there is external forces, then if you look at my previous video on the frequency response, first you have some transient response, which was not discussed in that video. And then after that transient response is damped out and go to zero, then we have the steady state harmonic response. So in that uh, harmonic or frequency response, we only looked at the steady state portion of the behavior. We never looked at the behavior of the system before reaching there, which is that transient one. And this is what we're going to do today. So here is the string of the guitar. This is the same example I used for one of my modal analysis examples. If you look at my video on modal analysis, I had a beam and I had the string of the guitar. So here is that the string of the guitar, and I'm going to give it some initial condition, which is like plucking the guitar, right, at any point, and moving it up, and then let it go, and then you know that it is going to vibrate, right? And then based on the damping in the system, it is going to slow down, and finally all of that initial condition will go to zero. That energy will be dissipated by the damping, right? So if we want to simulate this behavior, how do we do that? Well, the first thing is we need to have our static structural analysis as well as the modal analysis. Then we can do what? We can do the transient response. And you might say, why do I need both of them? For modal analysis, I understand, because transient response, as we said, is a function of the natural frequencies of the system. The output is a function of natural frequencies and damping and everything and the mode shapes. So I definitely need to have modal. But what about the static structural? Because clearly the transient response is a dynamic behavior. It's variable with respect to time. So why do I need the static structural? And the answer is that initial condition that you need to provide to this string, right? So bringing it to a specific location, let's say move this middle point up a little bit, right? So you deform the shape of the string, and then what? Letting it go. So before you let it go, that initial shape is what? Is a static deformation, because you applied some force, let's say in the middle, or apply some displacement, and then based on that the total shape of this string would change, right? If I move the middle point, the rest of the string would also what? Would also change shape, right? It's not going to stay straight, it's going to go up a little bit and then go down. So if I want to get that initial shape when I just moved one of the nodes up, that initial shape comes from what? From static deformations. So to provide that, I need this one as well. The other thing is this string right now is only one single object. If I want to see that deformed shape when I move one of the nodes, I need to divide this string into several sections so I can get what? I can get the relative displacement with respect to each other, and I can see the deformed shape. So the first thing I need to do is to break this line into several edges, into several line segments. So before I can do anything, I need to go and modify the geometry. This portion here is exactly the same as what I showed you in the modal analysis. This is the exact same thing. But as I said, for transient, I need to go here and I need to add several sections to what? to the string so I can provide the initial shape. So here you see it's single object, it's one object here. If I want to split this into several segments, I go to Concept, Split Edges, and then I choose this edge or line. And here, instead of definition fractional, I change it to definition split by n, right? And then I say, I want you to bring it down into 8 pieces or 10 pieces or as many pieces as I want. The more pieces you use, the better or the closer the deformed shape will be for initial condition compared to the real case. But of course, it is going to what? It is going to take more computations. So here, let's say I want 8, and then as I said, I selected this and applied it, and now I say generate. And now if you look, now I have what? Now I have 8 line segments, right? You clearly see that. It broke it into 8 pieces. So now I need to go and I can update my modal analysis here, or I can create a transient, and then inside the transient, which is going to use some portions of the modal data, I can update everything over there, right? So here I go to the what? To the transient structural. And all I would choose is the first 3 of these tabs, okay? So I use the engineering data, geometry, and model, and then I go to the setup. And it is going to update this portion for static structural and goes into transient. Okay, so now I am in what? In the transient. And you see I have all of these segments. Now, the first thing is this, that if you remember, I had a fixed support on one end of the string. On the other end, I had a displacement which allowed it to move along the longitudinal direction x, but remove the y and z directions, right? The displacements, as you can see, 0, 0. And then I had a tension force of 387 newtons as we calculated, so that the first frequency of the system is 440 hertz, right? So I had these 3, and they are under what? They are under static structural. But the transient simulation also need to have these 3 conditions: this fixed support, this displacement, and this force. So what I will do is, first I grab these 3 and drag them and drop them under what? Under the, see if I can do that. If this guy goes down, and then drop them under transient. So transient also has what? Also has those 3 conditions. They want to use the same conditions. That's the first thing you do. The next thing you want to do is, now, since I broke the string into what? Into 8 pieces, you want to regenerate the mesh and you want to redo the modal analysis, right? So here the mesh is done. The static structural, if it's not completed, you are going to go ahead and complete it for now, and as well as the modal. So let's just update the system before we get into the transient, okay? So here our system is updated, right? Now it's time to what? It's time to work on basically the settings of the transient, as well as to apply what? The displacement, the initial displacement, right? So we assume that we give it some initial displacement by moving one of the nodes up and then releasing it from 0 velocity, okay? So what are the things that we need to do? Everywhere that you see here, there is a question mark. You have to take care of it. So if I go under analysis setting, here it asks me how many steps do you want? And here I want 2 steps. What are they? The first one is the time from 0 to some time that I only move this from this perfectly flat to what? To the initial condition. That is my first step. The second step is starting from that initial condition to what? To a little bit time afterwards, so I can see what? The transient response. So here I choose 2 steps, okay? I choose 2 steps instead of one. And again, the first one is from 0 to initial condition. The second one is from initial condition to the time that I want the end of the transient simulation. Now, for the step number 1, it says, what is your end time? And here I choose a number, let's say 0.1 second. So in 0.1 second, I change my system from flat to initial condition. And then it says, what is your initial time step, minimum time step, and maximum time step? And here I choose a, the other thing is auto time stepping. Since this case here, you're going from a static condition, which is right now, to another static condition, which is initial condition, you are really not doing anything that is varying with time. You're just setting up the initial condition, right? In other words, your calculations are really static calculations. You are not changing anything with respect to time. You are just setting up what? The initial conditions. So I really do not need the system to automatically basically change my time steps, right? I can turn it off. And the other thing that you need to do is a time step. And here, as you can see here, it says the time step should be equal or less than this 0.1. So here I choose half of that, 0.05. And the other thing I want to do is this time integration. This time integration is done when the system's behavior is dynamic behavior. Since in the first time step from 0 to 0.1, nothing is changing, everything is static, I turn this off. This will change my dynamic response into a static response. There is no time integration done. The system is pure statics. Do I need to have large deflections? Yes. In the case of a string of a guitar, there is always the chance that what? You have a large, basically, displacement or deflection. So let's keep this what? Let's keep this on, right? So far, what do I have? So far, it's just going from beginning to the initial condition. Now, I need to look at what? Look at the time from 0.1 to the next time point where the transient response is really happening. So how do I provide the data for the second time step? This time, I change this current step number to what? To 2. So now I'm talking about the second time step. What is the end time? Remember, the start time is 0.1. So how much time of simulation do I need, right? How much? So here I just use 0.08 of a second. So I go from 0.1 to 0.18. Okay, from 0.1 to 0.0 to 0.18. So in other words, 80 milliseconds. That's all it is. 80 milliseconds is the second time step during which I want simulation. And you might say, why that small? Why just 80 milliseconds? Well, the reason is dynamic calculations like this, transient response like this, they are extremely time consuming and they take a good amount of time to be solved. Okay, so here I choose a small time, so I should not just be waiting here for some good time before I see the results. If you want, feel free to make this a little bit bigger, but be prepared to sit down and wait. Now here, I definitely need to have what? I definitely need to have the time integration on because this is a dynamic simulation, right? The other things that you want to do is the auto time stepping this time should also be on. And the steps that you take should be much smaller than what? The 0.08, which is the total time of the transient. So here, for initial time step, I use a very small number, and I use basically 0.0001. I use basically like 0.1 of a millisecond. 0.1 of a millisecond. Remember, the total simulation is 80 milliseconds. So here I have 800 points basically. If I go with this initial time step, I will have 800 time points for the transient response to solve. And typically what you set is the minimum type step is an order of magnitude smaller than your initial time step. So here it's going to be 0.01 of a millisecond, and then your maximum is 10 times bigger than the initial time step, which is basically 10 to the negative 3, right? So that's this guy, right? So initial time step here, I chose it so that I have at least 800 points, and my minimum and maximum time steps are 1 order of magnitude smaller and 1 order of magnitude larger than my initial time step. The time integration should be on, the auto time stepping should be on, and the large deflection should also be on. Otherwise, you are not going to be able to necessarily get the results, because the results could be nonlinear in this case. So here you see the analysis setting is done. And again, I go from 0 to 0.1, pure static simulation to set up initial condition. Then I go from 0.1 to 0.18. This is the time during which I look at the basically transient response. Now, what's next? Is there anything else that we need to do? Well, absolutely. What is that? That's that plucking, right? I need to move one of these nodes up and provide the initial condition. Remember, this displacement here is just at the end to not allow the end of the string go left and right, up and down, right? You need now to provide what? You need to provide the initial condition. So for that, you need to create what? You need to create a displacement here. So what I need to do is I right click here and go to insert, and then I say what? A displacement. And now what do I need for this displacement? First, I need to apply it somewhere, right? So where is it that I need to apply it to? So here, I'll try to choose the middle point of this string. Let's say I want to apply the initial condition to the middle point. So this is the first one, this is the second one, third one, and fourth one. So it's a point here. And to make sure you only select the point, activate the point filter. So here is the first, second, third, and right. Again, let's make sure this first one, second one, third one, and fourth one. So it should be right there. And so here, if we choose this point, we're going to apply our displacement to that point. And then what kind of motion do you want? You definitely want the motion to be along the y direction. You want x and z to be what? 0, right? Because you don't want any motion along any of those axes. So let me go ahead and kill those motions. Now for y, instead of providing a number, you want to provide a what? You want to provide it with a table. So here you go and say I want tabular values, right? Now here I add one extra point at 0.05, and remember this was the time step for the first part of the simulation, the static simulation. So initially I set my y to 0, but then at this time step I reach it to the final value that I want, and here I assume that I want to move that point 10 mils up, and then keep it at 10 mil, right? So here, this is going to be the data that I provide for the y motion of the middle point, basically moving the middle point 10 mil up and then let go. Now you might say, well, here you are not letting go. If you look at your displacement, it's also 0.1, 10 mil, it's also 10 mil between what? Between the beginning of the transient motion, which is 0.1 of a second, and the end of the transient motion, which is 0.18. So ideally, this portion of this y motion, this portion here, should not be here. Because if it is, it doesn't mean I'm releasing what? The initial condition. If it always stays at 0.1, then it's not going to move. I should let go of my initial condition. I should release the string. So what should I do here? This is where you need to deactivate this last portion of the data. So you right click here and say deactivate at this time step. Okay? And what does that do for you? It makes basically, right? You see, I can activate or I can deactivate a point. if I consider a point and deactivate it, there we go. If I deactivate it, you see that this displacement after the time of point 1 is not there anymore. That is equivalent to releasing the string. Good. So now my displacement of the middle point is all what? Taken care of. And the next thing I want is to go ahead and see what I want to see out of this transient. So I right click here and I can say what? I want to insert a total deformation, right? Or I can see anything else. So this is going to be the total deformation. But if I want to see, for example, the deformation of this middle point after you let go, you can insert what? You can insert a probe of deformation. So you can go to here, you can say insert probe deformation, and then it says, okay, where is it? And you say, well, this point here, right? I want to look at the displacement of that point over time. And then it says, do you want all of the motions of that point? You say, no, I just want the y-axis, because everything is happening about the y-axis, right? So now that's what? That's all you need to see, the overall displacement and the displacement of this point versus time, which you did using a probe. If you want to see that the system is converging, you can go under the solution information and change the output of the solution to what? To, for example, convergence of force or convergence of any of these parameters that you want to see, or displacement convergence. So let's look at, for example, the force convergence. Then go ahead and click on solve here. I did it and it didn't take too much time because my time step was small. Remember, the whole simulation time was just 80 milliseconds, and I made sure that the simulation does not take forever, right? So now if I look at the deformation of the probe, it is going to show me what? The displacement of this point, and you clearly see this is damped vibration, right? You see it is vibrating and it is being damped. If I allow this time to go a little bit further, you see that probably it is going to settle down at 0, right? So you clearly see the transient behavior here, damped vibrations, right? Or under damped behavior, basically. And if you want, you can look at the total deformation here. And if you want, you can also look at what? You can also look at the animation. So you can click on the animation, but what I recommend for you is you make it slow, and then you also under contour make sure this solid fill is active. And if you do it, you can see what? You can see that deformation here, and you see that the amount of vibration is going down. As you can see, it's slowing down because the damping is killing the energy. So I can redo probably the same thing, but I increase this time. Instead of 0.18, I make it like 0.25, 0.3 or something, and see that this guy is gradually what? Stopping. So here what I did, I changed the final time of simulation at 0.3 seconds. So now I'm doing it for 200 milliseconds and 2000 data points. And this is the probe. As you can see clearly, it is extending, and finally it is settling down at what? At 0, because I gave it enough time to basically completely be damped out, right? And if I look at the animation this time, right, let's see. You see that the string is vibrating, and ideally it should slow down, and there we go. You see, now it's all flat. It's not moving anymore, right? So you clearly can see that here. Let me show you in 3D, right? It is vibrating, 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 and then there we go. The vibrations are killed out. So this is a simple transient response that when you play guitar, you're exactly doing this. You're plucking the string, giving it an initial shape, letting it go. And what it does, it gives you a combination of what? A combination of the mode shapes and a combination of the natural frequencies, right? And it's the combination of these frequencies that will give the sound of the guitar what it is, right? It gives it that specific tone, basically. So hopefully the video was useful to you, and I will see you in my next lecture.